Okay, so as promised, here's the intermolecular forces video. You should know what you're doing for this, but I can understand, kind of forgetting it. It's an important concept to have because it kind of explains all the properties. Usually attached to this, I talk about liquids and their properties. I'm not going to do that. I'll talk about boiling point briefly, but boiling point's a good measure of the strength of intermolecular forces. But I'm not going to talk about viscosity in this. I'm not going to talk about, surface tension or vapor pressure, which is also an important one to know as well. But let's talk about intermolecular forces. So first of all, every single force that holds any chemical together, whether molecule or atom, is always an electrostatic force. So electrostatic is the interaction of positive and negative. So positive, some amount of region of positivity or an ion or something, or a region of polarity or something like that. And then a region of negativity, and they're attracted to one another. So interaction between positive and negative. So I'm going to call this an electrostatic attraction. So it's the interaction between a positive and negative. Every single type of bond that you have ever discussed in chemistry is some version of that. And so let's just talk about the intermolecular forces, so things between atoms. So if we have a little scale, on one end of the scale, I'm going to have ionic bonding. Ionic bonding is defined as a transfer of electrons. So it's a complete transfer of electrons. I've got two atoms, one electron is transferred to the other, and we turn into, well, because the one that lost the electron becomes positive, the one that gained the electron becomes negative, like fully negative, because now it has that extra electron. And we have this positive negative interaction, this electrostatic interaction between those two ions. So we have this ionic interaction. Okay, so that's one extreme where the electrons between two neighbors are completely transferred. The other extreme is a covalent bond. In a covalent bond, what you have is you have the same type of setup where you have an electron. We're actually going to do two electrons, and instead of a transfer of an electron, they kind of just share between the two of them. Okay, so they're going to share between the two of those. All right. So if we had this interaction between two shared electrons, what it really looks like, and this is kind of how a covalent bond actually works. Maybe you remember this. If you remember, if I have a positive, a little bit smaller than that, let's see. So if you remember, we have something like a positive nucleus, and I'm going to have another positive nucleus. So this is kind of like the ones above here. And they each have an electron too. Let's put the electrons here and here. This is how a covalent bond works. So you can imagine that, first of all, any like charges are going to repel one another. So the positive can't get too close to the positive. Those are going to push back. That's going to be repulsion. Those electrons are generally going to want to stay away from one another. Those black lines are going to be repulsion. But we also have the attractive forces between the nucleus and the electron. You have the attractive forces between the nucleus and the electron. Okay, so these are attractive forces. So those two things together, again, these electrons are kind of shared in between the two, and they don't belong with either one, but the overall shared attractive forces outweigh the repulsive forces, and it creates an interaction. It is, I want to point out the fact that it's still electrostatic. Negatively charged electrons are attracted to positively charged nuclei, and it creates this overall interaction which holds those things together in a shared state. Okay. So at one end, I've got ionic, the other end, I've got a covalent bond. And it's important to recognize that way over on the right, this thing is considered non-polar, right? There is nothing in between, or when they're equally shared, neither of these two atoms are going to have a greater pull on the electron than the other for the perfect covalent bond. On the other extreme, we have ionic. We have a transfer of an electron. So it goes all the way from nonpolar, where it's complete sharing, to complete transfer of electrons over here with ionic. Well, in between, before we get all the way to ionic, we are going to have a polar covalent bond. And a polar covalent bond is going to be similar. Again, they're going to be sharing. One does not own the electrons. Nothing owns the electrons, but the interaction between these two are there. If that's the two bound atoms, okay, similar situation to the repulsion and attractive forces that we have over here. It's just one of them happens to actually have a greater electronegativity. So the electrons prefer to be on the, in this case, right-hand side, right? And over here, oh, I had that back. No, I've got this right, yeah. And the positive is there. So in this case, this atom happens to be more electronegative. And it has a greater attraction to the electrons on that side. So you kind of get this uneven sharing of electrons. You can imagine the electrons are kind of over here a little bit. So again, those attractive forces are there, the repulsive forces are there, but the electrons are kind of shift in this direction in terms of if that were a cloud of the electron density. So these are the things that hold atoms together, hold molecules together. So now we're going to start talking about a different thing. So here we have a covalent bond, which is intramolecular. But between two atoms, we are going to take a look at the intermolecular forces, which is going to be between molecules. So between molecules, we're always going to have intermolecular, and we're going to focus on those. And I am going to call intermolecular forces I'm going to shorten it with just IMF. So anytime you see that, that's what I'm writing. It's important to mention that just like all of bonding, all intermolecular forces are electrostatic. It is some version of positive and negative attracted to one another. We're going to focus on three. Three are relatively important. The van der Waals forces, which is hydrogen bonding, dipole, and London dispersion force. Just to give you an idea, a hydrogen bond is about 10% the strength of a covalent bond. So these things are weak for the most part, but they can actually get pretty strong. And the London dispersion forces, although they seem the weakest, the bigger things get, the more pronounced those become. So London dispersion forces are actually incredibly strong in things like oils and fats, where these molecules are, tens of thousands of grams per mole. Okay, so massive numbers. So we're going to focus on the van der Waals forces, and we're going to take a look at all of the different options for intermolecular forces. So let's take a look at intermolecular forces and ultimately how they're going to affect properties eventually. Okay, so what I want you to think about is there are three types of molecules we can have. We can have a nonpolar, I can have a polar molecule, and I can have an ion, just like I discussed above. Those are the three choices. So again, I can have nonpolar, I can have polar, and I can have an ion. Okay, so the types of interactions that we're going to talk about are just interactions between the different combinations. So let's start with nonpolar. Nonpolar can be combined with another nonpolar. Nonpolar could be combined with a polar, and nonpolar could be combined with an ion. So that takes care of all of the options for nonpolar, all of the potential interactions. A polar could interact with a polar. It could also interact with a nonpolar, which is above, right? So polar, and then it could also interact with an ion. So polar interacting with an ion. I'm not going to repeat any if I already have a nonpolar polar. And then finally, an ion can interact with an ion. And that's pretty much it. So if we take a look at these, that's all the different combinations that we have. Nonpolar with the 3 different types, polar with the 3 different types, and then ion with the 3 different types. So these are the 6 combinations that I can have. The ones that are important are nonpolar, nonpolar, polar, polar, and to a lesser extent, polar and ion. We're going to see this a lot when you actually talk about dissolution. But when you dissolve a water, or I should say, not dissolve water, dissolve salt in water. Yeah, so when we dissolve salt in water, salt in water. Okay, there we go. And of course, we'll talk about that briefly when we talk about that combination, but dissolving salt in water gets pretty important when you're talking about energy. Okay, so let's take a look at these different combinations. We're going to throw one out right away. Ion and ion-ion interaction is known as ionic, right? That's an ionic interaction, so positive and a negative interacting. Again, that's electrostatic. It is incredibly strong. But the problem is, it is an intramolecular force. So it doesn't really count as an intermolecular because it's between ions, which kind of counts as an intramolecular force. Okay, so let's move on to the other combination. So we're going to kind of eliminate that one right off the bat. Okay, so let's take a look at one of the most important ones and one of the ones that's hardest to kind of understand. So first of all, before I continue, I am going to talk about melting point and boiling point. Mostly boiling point, but melting point and boiling point are a great way, or kind of a direct measure of intermolecular force strength. Meaning, if I have a higher boiling point, that means that I have higher forces or higher intermolecular forces holding them together. Right? The greater the boiling point that we have, the better that they're held together. And it's always a competition between the heat of the room or the heat of the environment and the energy of the environment, as well as the forces holding together. So if those forces are really holding together well, we're going to have to really crank the temperature up in order to get them to break apart and become a gas, or to become a gas. Okay. So let's take a look at London dispersion forces. I'm going to start with a really simple demonstration. We'll talk about this little picture to the right, but I'm going to have three little circles here, and I'm going to say that, okay, this right here is, there we go. Okay. And we're going to do a couple of these. There we go. Close enough. Good enough. Okay. So I have these little 3 circles here. These are going to represent atoms. So these are going to represent neutral atoms, let's say with a handful of electrons each, or a few electrons each. There we go. So I don't have to draw it again. I'm going to copy that, paste. All right. What is keeping these electrons in these locations? Is anything keeping the electrons where they currently are? Not in a nonpolar compound. And it's something that is nonpolar. Essentially, again, these little circles could represent a molecule. They could represent an atom. They could represent a diatom, something like that. But they just essentially represent nonpolar. They represent something nonpolar. Okay, so nothing is determining where these electrons are. They're allowed to be wherever they want in these spaces. Okay, There's nothing restricting them just in terms of, there's nothing restricting them. Let's just say that that's what a nonpolar is. Nonpolar, something that's polar would be, all right, well, all of the electrons have to prefer to be on one side, and therefore they have to pile up in one location. There's nothing that's kind of restricting these electrons to any degree. Okay, so with that said, at any given moment, you could have electrons just happen to pile up on one side of that central atom, let's say, all right, that center atom there. Again, these are intermolecular interactions. That center atom, all of a sudden the electrons just pile up. So this just happens in an instant, next instant, okay? Because all of the electrons have kind of piled up on the left-hand side, let's take a look at what's going on. Well, if all the electrons are over here, it kind of makes this side of the molecule partially negative. Electrons are negative, they're piling up on the left, and therefore it's negative. If the left side of it's negative, equal and opposite, we've got to have a positive side as well. So the left side is negative, the right side is going to be slightly positive. So the question ultimately is, how do we expect its neighbors to interact? So if all of a sudden this positive appears here, what are these electrons going to do? They're going to kind of rush over towards that positive charge. And the electrons from the neighbor are going to pile up over here. And what that does to this atom is it creates a partial negative here, partial positive there. And that is the most important thing about these London dispersion forces. I have a positive and negative that are now next to each other, and I have created that interaction. So there is our first London dispersion force, LDF. London dispersion force formed because of that moment in time when one is partial, it was just happened to be negative and the other side happened to be positive. Just like the right side, these electrons are going to sense the presence of this negative charge, and they're going to run in the opposite direction. They're going to get away from that negative charge, moving over here. Again, this creates a partial positive on this side, partial negative, and we have another London dispersion force interaction. Okay, so that's it. That's what happens with these. That's what happens with these things. So that's how these things actually form. Is essentially they run into a situation where we have just at some random instant, you get those electrons in the center one to move one way, and they all shift in one direction. What happens? Are they required to stay there? I mean, it's good. We've got positive and negative interaction, which is an electrostatic interaction, but there's nothing holding them there. So at the next instant, I could get all of the electrons to pile up, end up piling up on the other side because some other atom in the bulk material shifted, creating those interactions, creating those positive and negative charges, right? So that's negative, positive, negative, positive, negative, positive. So that's the next instant. So there's just this kind of shift back and forth in the bulk material. It just kind of waves back and forth, left and right, up and down, back and forward. You just keep getting these movements back and forth, and the electron, one of them changes, and then everything cascades around it. And then some other one changes somewhere else in the bulk material, and everything else changes. So that is intermolecular forces. Those are the things that are holding us together. So to sum up intermolecular forces, so number one, what do you take away from this? The increase in molar mass equals an increase in London dispersion forces. So the higher the molar mass, the greater the strength of the London dispersion forces are going to be. Okay, so the higher the molar mass, the greater those London dispersion forces are going to be because there's more electrons there to kind of interact. If we run into the same, if the molar masses are similar, we're going to look at something a little bit different. We're going to look at the surface area, an increase in surface area equals an increase in London dispersion forces. And I'm going to show you what I mean by that with an example. Okay, so we're going to take a look at a simple compound called butane. which you would see in something like a lighter. Butane looks like this. That's 4 carbons in a row. This is butane. For all intents and purposes, it's just kind of this long chain. So it kind of looks like that. Okay. Isobutane. This is, again, 1 carbon in the center, 3 carbons around the edges. This is known as isobutane. These things weigh the same exact amount. This is more spherical than cylindrical and lengthwise. And so this is what we've got. If I line a bunch of butanes next to this, they're going to line up like this, and we're going to have these interactions here. We're going to have these interactions here. With the isobutane, we're going to do the same exact thing. The neighboring isobutanes creating interactions would look something like this. But now the interaction is quite a bit reduced because there's less contact, there's less surface area for those things. Okay. And this shakes out. Remember, again, boiling point is a measure of intermolecular forces. So what that means is if I have a higher boiling point, I have stronger forces. So if surface area goes up, London dispersion forces go up. So I'm expecting this to have a higher boiling point because it's got more surface area. And it does, in fact. The boiling point of butane. The boiling point of butane happens to be 0 degrees Celsius. The boiling point of isobutane is -12 degrees Celsius. So that makes sense. This has more surface area leading to a higher boiling point than this leading to a lower boiling point. Okay, good. So that is London dispersion forces. So let's take a look at my picture over here on the right. So I can't center it more. I probably should move it. But what I have here is chlorine, bromine, and iodine gas. Okay, so we're chlorine, bromine, and iodine. If you look at your periodic table, take your periodic table out and check it out. Chlorine, bromine, then iodine on the periodic table, right? That is what it looks like, the order on the periodic table. So chlorine weighs the least, has the smallest molar mass, and it is a gas at room temperature. Bromine is the one in between. It's a liquid at room temperature, and iodine is a solid at room temperature. What that says is the reason that chlorine is a liquid at room temperature, or I'm sorry, a gas at room temperature, is because its intermolecular forces are not that strong. The reason that iodine is a solid is because it has very strong intermolecular forces. Again, this is true because these things here are only bonding through London dispersion forces. So as the mass gets bigger, we notice that we go from gas to liquid to solid. If it is a solid at room temperature, it means those forces are stronger than the temperature trying to pull them apart. Again, it's that competition between the two. Okay, good. One last conversation I want to have about London dispersion forces is polarizability. This idea of polarizability is the ability for electrons, or the electron cloud, really. Oh, I don't know why I just lost that. I'm going to give it a pause for a second. Okay, so to get back to it. So polarizability is the ability for electrons to displace their shells. So ability for electrons to displace from their shells. You don't really hear much about polarizability anymore. In fact, there's an old term. So if here's my 2 compounds, or 2 ions. If they're very concentrated, and if this doesn't shift all that much, if it stays about the same size, or there's not much shift in electrons, this would be known as a hard atom or ion. And if you had something that was very polarizable, okay, so you might have something like, so let's see, how do I say this? Yeah, okay, let me do it this way instead. So you can imagine that I have some, non-polar substance, and I bring a positive charge next to it. If it is hard, as in it stays pretty concentrated, you're not going to see much shift. So if that's the center, you're not going to see much shift at all from the center. It's going to pretty much look exactly the same at the end. So there's a very low polarizability in this. If I have something that has a high polarizability, this is generally when they're larger in size, and I bring a positive next to it, what you might end up seeing is the electron cloud kind of heads in the direction of that positive charge. This would have high polarizability. Okay, great. So that's what we've got. That's the first one. That's the longest one. That's the interaction of London dispersion forces. London dispersion forces come out to molar mass. If I have to separate based on molar mass, we're looking at surface area as kind of the backup that if we're put to the test. Okay, next up, let's talk about dipole-dipole interactions. So a dipole-dipole interaction is when things have permanent dipoles, so polar molecules. So we have to identify these things as having polar molecules. And so if I start with something like, let's say HF, here's the Lewis structure of HF. Actually, probably shouldn't even use HF. Let me use, yeah, I guess HF will work. HF will work, okay? And so we know that the fluorine pulls the electrons to it. And over here, I have this positive charge. Over here, I have this negative charge. And ultimately, what this thing really looks like is you have a negative on one side and a positive on the other. So if I have a bunch of these in solution together, and if they're in solution, they're kind of just randomly placed around. So positive, negative, sure, positive, negative. I'm just putting a bunch of these around randomly. Okay. So what you end up having is you have a bunch of, just like we were talking about before, you're going to have a bunch of these things that are going to be repulsive. So anywhere you have a similar charge nearby one another, you might have repulsion, right? But equally, we're also going to have a lot of the other version of that, which is going to have a lot of these good like interactions, which is going to give us a lot of attractive forces. Okay, so those forces right there, so again, those are attractive, those are repulsive. The strength of those is going to depend a lot on the strength of the dipole. So ultimately, it comes down for this one, what you need to know is the stronger that partial positive and partial negative, okay, equals an increase in polarity. An increase in polarity equals an increase in what we call dipole-dipole interaction. Okay, so that is really what we're looking at. So let me just sum it up down here one more time. So an increase in polarity, and an increase in polarity is the change in electronegativity. That's really what we're looking at. How big is that gap? Equals an increase in dipole moment. Dipole moment is mu. It's how we measure the difference essentially in polarity. It's how we measure polarity. So dipole moment can be measured. So increase in polarity equals an increase in dipole moment, which equals an increase in dipole-dipole interaction. Which equals an increase in intermolecular forces, which ultimately means we have an increase in boiling point if that's the property that we're looking at. So that is kind of the overall gauge of, all right, if I have to choose between two with dipole-dipole interaction, which one happens to have the strongest pull? Okay, which one is the strongest dipole? That's going to give us the best answer. And we can see that here. So if we take a look at this, here I have, notice that they're all about the same molecular weight. Okay. These are their dipole moments, the measure of their dipole moment. We see that we're going from left to right. We have an increase in polarity as we go to the right. And what happens to boiling point? Boiling point is increasing as we go from left to right. So increase in mu, or polarity, equals an increase in intermolecular forces in the form of dipole. Stronger dipole forces equals an increase in boiling point. Again, they all have a similar mass, so it's not London dispersion forces that's separating these things. Okay, next up. Once we check, first of all, everything has, and I don't even think I said that, so let me go back and absolutely say that. Everything has London dispersion forces. All atoms, or all interactions, intermoleculars, has London dispersion forces. Every single one is going to have London dispersion forces. So if I'm trying to decide what forces are present, London dispersion forces is always the first thing that I write down. Everything has London dispersion forces. It only has dipole if it's polar. So the first thing we check is, okay, it has London dispersion forces. Is it polar? If it's polar, yes, it has dipole. And then the next is it capable? If it has a dipole, it must be polar in order to be able to do the following. In order to have hydrogen bonding, it must be polar. So check and see if it's polar. It has London dispersion forces. If it's polar, it has dipole. If it has dipole, we check to see if it is capable of hydrogen bonding. Hydrogen bonding is, so what is required for hydrogen bonding? One, you need a lone pair on, and when I say a lone pair, it's those two electrons on a nitrogen, oxygen, or fluorine. Generally, you always have this, but that's a good thing to check. Two, you need a hydrogen attached to nitrogen, oxygen, or fluorine. And in fact, this is the most important one. And so you can probably pretty much just look for this. But you do have to have that lone pair in order for those things to be attracted, and I'll show you why in just a second. So what this looks like is, if I have my compound XH, where X is equal to nitrogen, oxygen, or fluorine, and I have another X nearby, and I don't care. And by the way, whenever I say R, an R group is just some organic group. So it's just some organic stuff, carbon, hydrogen, nitrogen, who knows, but it doesn't really matter. It's just some other stuff. So if I have nitrogen, oxygen, or fluorine, we have, and I can use this, we have this massive dipole that forms, okay? We have this really large dipole that tends to form. Okay, so it's really kind of big. Okay, so we have this really large dipole that forms, giving us a partial negative here and a partial positive here. Now, just think for a moment what the makeup of a hydrogen atom is. A hydrogen has one electron and one proton in its nucleus. So the hydrogen atom is sitting here with its proton in the nucleus, and its one electron is hanging out in this bond. That means this entire side right here there are no electrons there. In fact, the electron is not even there. It's even closer to that X because that's really highly electronegative. So this entire side over here is very positive because there's no electrons in the way. So it's like a bare proton just waiting to interact with whatever comes near it. That's why it's so strong. Okay. All right. So once I have this, we are going to have a bond that forms between that very barren positive charge and that lone pair of electrons, because again, the electron density for this is pushed towards X. Okay, so that's kind of the shape that we take. When it comes to bonding, what we're going to look for is if the number of bonding sites, hydrogen bonding sites, equals an increase in intermolecular force strength. Okay, so the more hydrogen bonding sites we have, the stronger that interaction is going to be. And I think I have one example kind of showing you a handful of those. Okay, all right, good. So other combinations. So these are lesser used because generally we're talking about something with itself, which is generally the polar-polar, non-polar, non-polar. So we never really talk about these other combinations. So if I have a non-polar with a polar, okay, so putting a non-polar with a polar together. So here's my non-polar. And here is my polar molecule. Okay, so you can imagine, and I think this should work. So you can imagine what happens if I take this polar molecule and as I bring it closer, how are those electrons going to respond? Okay, so as I bring it closer, how do those electrons respond? Well, as we bring this thing closer, those electrons are going to start to move in the direction of that positive charge, right? They're not going to run away from it. So we expect those electrons to kind of line up and create this partial negative on this side, partial positive on the other, because we want to have that interaction, right? So that's what those electrons are lining up to do, to create that interaction. We call this a dipole. Again, that's from the polar part. We always put the more polar one first. A dipole and an induced dipole, non-polar. Okay, dipole induced dipole is the name of the force. So you have essentially a dipole that is formed by the presence of that permanent polar molecule. So it kind of forces it to happen. Okay, so same question about what happens if I interact a nonpolar with an ion. Well, if I bring that ion close, what do we expect to happen is, again, we expect those electrons to kind of line up and interact. So I have this partial negative on this side, partial positive on that side. We have created this interaction. We are going to call this an ion. We always start with the first one keeping its name, ion induced dipole. Again, that dipole is induced by the presence of that permanent plus charge. And then finally, this last one, polar and ion interaction, we are simply going to call it, I'll name it first, an ion dipole interaction. And we see this all the time whenever we dissolve something. It creates this little shell around an atom. This is called a solvation shell. It's a shell of water around the outside. Okay, so if I have the interaction between a positive charge and a dipole, you can imagine a bunch of them are going to line up around it. Okay, and so on and so forth. And water does this all the time. That's how things actually dissolve. We call this an ion dipole interaction. Okay, good. All right, so properties of liquids. Again, boiling point is the most important thing. I guess I'm just going to skip down to one of these problems. I think that'll do. When you have a problem like this, I guess I could do this one quickly. No, I'm not going to do this one. You just list the properties, or you list what these things have. So this is my CH3. This is a nonpolar molecule. It has London dispersion forces because everything does. And because it's only nonpolar, it doesn't have anything else. The next one is two chlorines attached to it. It looks like they're on this side. So Cl, Cl, H, 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 H. This one is in fact polar. So I know it has London dispersion forces. It has dipole, dipole because it's polar. Does it have hydrogen bonding? It doesn't have nitrogen, oxygen, or fluorine, so it stops pretty much there. Next up, I have an OH on one end. I should have made these all way the same, but that's fine. This is polar because of the presence of that oxygen. So this is polar, so it has London dispersion forces. It has dipole-dipole, and it does in fact have hydrogen bonding because it has that. It does have that OH attached. And then finally, the last one, OH on both ends. This is the same exact situation. It's polar. It's got London dispersion forces. It's got dipole-dipole. It has hydrogen bonding. So which of these is the highest boiler? Or I should say, yeah, which of these is the lowest boiler? Let's start there. This is going to be the lowest, and we're going to rank this as 4. That's last because it has the least number of forces holding it together, the weakest forces holding it together. The next would be, this one would be next because it has dipole-dipole, but it doesn't have hydrogen bonding. And now we have 2 that we have a choice between. Which of these is going to be the highest boiler? Well, this one, the one in the lower right, has 2 locations for hydrogen bonding. This has 1 location. So we expect this one all the way to the lower right to have the highest boiler, to be the highest. So we'd rank that 1, and this one would be 2. Okay, so that's kind of how we do these problems. It's the same way with solubility, which one has the most like forces of whatever it's dissolving in, and that's how you do that calculation. So that should do it. That should give you some idea of how to do intermolecular forces again, and I hope it helps.